Okay, this one's Giancoli Physics AP Edition, 7th edition. We're working on problem 50 in chapter 10, fluids. Go ahead and jump into it. This problem reads, a 6 centimeter diameter horizontal pipe gradually narrows to 4.5 centimeters. When the water flows through this pipe at a certain rate, the gauge pressure in these two sections is 33.5 kilopascals and 22.6 kilopascals respectively. What is the volume flow rate? So go ahead and pause the video, take a few minutes, see if you can set this one up. Come on back and compare notes. Okay, let's see what we're dealing with here. As usual, we're going to identify the values we're working with. In this case, there's a lot going on. I'm going to draw a picture to keep track of things. I have a 6 centimeter diameter horizontal pipe that narrows down to 4.5 centimeters. So if I draw a pipe here, it's narrowing. Certainly not to scale. Now, because I strongly suspect we'll be dealing with the area of the pipe here, before I get too deep into this and forget the quantity that I'm dealing with, I'm going to go ahead and split that into the radius now. So that's going to be a radius of 3 centimeters, which I'm also going to convert as we go to 0.03 meters, just to try to avoid some oversights later. And similarly, on the other end, that's going to be a 2.25 centimeter. We'll call this radius 1 over here. We'll have radius 2 over here. That's going to be a 0.0225 meter radius for that portion of the pipe. In the same order, I've got a pressure over here. So pressure at point 1 is 33.5 kilopascals. Now, they tell us this is gauge pressure at both locations. That's just ignoring any common atmospheric pressure on the system. So we can compare these two pressures directly. We have 22.6 kilopascals over here. And as you'd expect, for a horizontal pipe, as the pipe narrows here, the velocity is going to increase. As the velocity increases, the pressure is going to drop. So this should make sense to us. This definitely looks like a Bernoulli's equation type of situation. Let's go ahead and grab that equation. I'm going to grab all of our equations. Move them in over here. And what we're going to have here is Bernoulli's equation. It's kind of a starting point because of the values I have included in my system here. But notice what they ask us for. They ask us for the volume flow rate, which again, depending on your textbook, may include V dot. But that's a volume per time, which can also be expressed, since volume is length times an area, this can also be expressed as a velocity times an area. If you break this volume up into an area times a distance, that's a distance per time times an area. So that's a velocity times an area, which you may recognize from our continuity equation down here. So we're going to be using this equation as well in this problem. But the values we're working with are included here. So we're going to use Bernoulli's equation with our velocities and the continuity equation to get from velocity to flow rate, because both of those expressions represent volumetric flow rate. So that's how we're going to get from Bernoulli's to the volumetric flow rate. We'll start making some substitutions. Let's start by applying our equation to our problem. Because it's a horizontal pipe, right there, it's a horizontal pipe, no height change, so we can eliminate a hydrostatic pressure due to height portion of the equation. If I move the pressures to the other side, we have our dynamic pressure on the other side. And that's just simply rearranging what's left here. And once we get here, we still don't have volumetric flow rate, but we can see that that is related to these velocities. So let's go ahead and work those in. Since volumetric flow rate is equal to the area times the velocity, I can express each velocity as the volumetric flow rate divided by its respective area, and just make both of those substitutions here. If I do that, I have 1/2 the density. Velocity 2 is going to be the common volumetric flow rate. Remember, this pipe is closed, so whatever goes in has to come out. So the volumetric flow rate is the same for both locations. But this will be the area 2, and that quantity will be squared. Same volumetric flow rate. Area 1, quantity squared. Now, area is easy enough to calculate. Since I have the radius, these are both going to be pi r squared in their respective locations. I know the density of water, and I was given both of these pressures in the problem. We can make these substitutions as we go. So basically what I need to do is factor out this volumetric flow rate from this expression and divide everything out. So let's go ahead and start by flopping the equation as I factor out the volumetric flow rate squared. If I factor out the volumetric flow rate squared from this portion of the equation, I get the volumetric flow rate squared, the thing they're asking me for. Yep. And the rest of this is the 1/2 density. That'll be 1 over. Now you got to be careful here because this is pi radius squared, and then we're going to square it again. Let's just do pi radius 2 squared minus 1 over pi radius 1 squared again. And that will all equal my difference in pressure between the two locations. Now I've got volumetric flow rate here. I just need to divide this pressure here by this entire expression, which looks pretty busy, and it is. Volumetric flow rate, I have to divide both sides of the equation by this, and then take the square root. I'm going to get a hot mess of an equation over here. That's pressure 1 minus pressure 2. I'm going to divide by this half over here that puts the 2 in the numerator. In the denominator, I have the density. And I have the inverses of these two. Now, I could factor out the pi squared, and that would be in the denominator of the denominator that would put it in the numerator. Let's go ahead and do that. We'll save ourselves a little bit of trouble. Put the pi squared up there. Then that leaves us with just let's put some brackets here. 1 over the radius 2 squared minus 1 over the radius 1 squared. Close our brackets off. Now I believe, check that algebra, but we now have the volumetric flow rate, the thing they asked us for up here. In terms of a pressure I know, a density I know, and a few radiuses that were given. So we should be all set. Ready to plug in our numbers. Again, this is a pretty busy equation, so be cautious, especially with the layered squares here. There may be other ways to represent this expression. I'm going to go 2. I'll put the pi squared over here because that's probably how I'll put it in my calculator. Pressure 1 was given as 33.5 kilopascals. Pressure 2 was 22.6 kilopascals. We have to be careful with our units here. With that K in there, that's 1,000, and the Pascal by itself is the SI unit. So very likely we'll need to enter this in our calculator as 33,500. And that's all divided by our density, which again, you can look that up. Or look in the table in the front of the chapter. 1,000 kilograms per cubic meter for water. And again, being careful with those squareds of squareds. radius 2, which is the location to the right, was the 0.0225. 0.0225 meters squared the other radius was 0.03 meters. Again, we're going to square that. We square both of these quantities afterward. Extend out our square root here. That is a hot mess. How I enter this in my calculator is a bit convoluted because I have a dinosaur for a calculator. We're going to go ahead and do that. When you do this, keep in mind, as I mentioned earlier, because these are all SI units, when I put this in my calculator, I'm going to actually enter 33,500 to make this just so pascals, and also 22,600 here. That way, this is all SI units, and they should all work out to give us a cubic meters per second. Because these are cubic meters, the SI unit per time is seconds. This is a volume per time, so we should get cubic meters per second. So go ahead and grab your calculators and see what you get. Okay, after entering that hot mess into the calculator, you end up with 0.008981-ish. And again, by converting those to pascals rather than kilopascals, and that all being SI units, we're going to get the SI unit for volumetric flow rate, which is cubic meters per second. We can convert that to a different unit if you feel like it, but again, they didn't really specify the units they wanted. And these are the SI units. We'll just leave that in that unit. Now, for these significant figures, we have 3 significant figures here, but we only have 2 significant figures up here. So we'll limit our final answer to 2 significant figures. Now, we round that. We're going to get 0.90. We're going to include the 0 to clearly communicate that we are out to 2 significant figures here. Even though that rounds to a 0 there, we're not going to lop it off because we need that to illustrate the significant figures. So our volumetric flow rate is roughly 9 thousandths of a cubic meter per second. That should take care of it for this problem. We're on to the next one.